Okay, hi, it's Mr. T here. In this video, I want to talk about free body force diagrams. We use these diagrams to solve most physics problems, as a start to solving physics problems, specifically ones that involve forces. So some general rules that we use so that our diagrams are consistently similar and we can use them to solve our problems. So let's go over those. So on the right here, you can see here's a picture of a car on a ramp. There are going to be forces acting on this car. We want to identify them and quantify them. That is to put their direction and their size. So that's what a free body diagram does. The very first step of the free body diagram is we put a dot where the center of mass would be. This is how we start solving them. Now there are actual 5 forces that we would use in a free body diagram in this course in level 2 physics. But so let's go over some of those. The first one is the gravity. We always have a gravity force on anything that we're looking at from a side-on view. Okay, from a side perspective, we're always going to have gravity. It's acting straight down. So we're going to draw a vertically down arrow, and we're going to label that as Fg, or sometimes you can use Fw, which is weight force, or Fg for the force or the gravity force. So I'm just going to call this Fg. That's our vertically down arrow. This represents the force of gravity acting on this car. Okay, so if there's a gravity force acting on this car, there's another force that's acting in response to this, and this is a reaction force. Now the reaction force always acts perpendicular to the surface that the object is in contact with. Now this car is in contact with the surface of that ramp. So we're going to draw an arrow that starts again from the center of mass and goes away at 90-degree angle from the surface of that ramp. And we're going to call it Fr. Sometimes we call it Fn, which is a normal force, which is again a normal force means a normal is a line that is 90 degrees to the surface. Okay, so the third force that we can draw here on this diagram is a friction force. Now this car was left to its own devices, would roll down this hill, and friction would be acting in the opposite direction of motion. If it's got its brake on, then friction is still acting against the direction that the motion would go. So we're going to draw that on here. Now the other thing about the friction force is it always acts parallel to the surface. So we draw it parallel to the surface, and there it goes. Now notice it's quite a bit smaller, and that's usually true when objects aren't traveling too fast compared to their mass. Okay, there are 2 other forces that we're generally going to use. One is a tension force, and another one is a centripetal force. Centripetal force we'll use later in the topic. Tension force we'll see in a couple of diagrams. I'll show you where we can use that. Okay, so let's have a look at the specific diagram. Here is a silhouette of a girl, and she is having a shot with a basketball through a hoop, and I want to know what are the forces that are acting on her. So when we draw our diagrams, we want to follow certain rules. And the first thing we want to do is draw the center of the mass, sorry, a dot at the center of mass. So this is the dot where all our force arrows are going to originate from. So I've drawn that, that's the center of her mass. Now I want to draw the force arrows acting from the center of her mass. So the first one I usually draw is gravity, because I know that, as I said, all objects have a force of gravity acting on them. So let's draw, I didn't draw that one first, but let's draw the force of gravity. There it is, acting straight down. And let's draw the force acting opposite to it. Now, the reaction force isn't always opposite to it, but in this case it is, because she's standing on level ground, so the reaction force is acting at 90 degrees to the surface she's standing on. So there's 2 forces. We've drawn them away from the center of mass. And the third point we have to note is the length of the arrow represents the size of the force. Now those 2 forces aren't the only 2 forces acting on this person, because she's about to push the ball, or she is pushing the ball so it will go towards the goal. There is an actual force that the ball is pushing back on her, and this is called a reaction force. and the reaction force compared to her weight force or gravity force is quite small, so that's the size of her reaction force. So remember, the ball has a force acting on it going directly up to the right. Newton's third law says every action has an equal and opposite reaction. That is, every force equal and opposite force. So if the ball has a force acting on it up to the right, she must have a force acting on her backwards and down. But it's a lot smaller than her reaction force or the gravity force. So we've got to make sure these are in magnitude. There's one more force that's acting on her, and that's a friction force. And the actual friction force is from the sole of her feet onto the ground, and it stops her from slipping backwards when she pushes the ball forwards. If she was actually on a frictionless surface and there could be no friction force, when she pushed the ball, she would have a force pushing her backwards and she would slip backwards or fall over. Okay, so that's the things we need to know about drawing a free body diagram. Let's look at some examples. Oh, sorry, one more thing. Okay, the FG, as I've said, always down. FR and FC are always 90 degrees from each other. So just check that they're always perpendicular or 90 degrees. Now remember, the reason for that is the R force is 90 degrees to the surface and the friction force is always parallel to the surface. Okay, so example. Let's draw a free body diagram of the forces acting on the child here. So here we've got a child being held on a swing at that angle. Let's draw the center of mass right there. Okay, what forces can we see acting here? Well, we know that there's a gravity force because we know that in all these situations there's a gravity force acting directly downwards. So let's draw that. Now, what is the reaction? There is no reaction force or push from the ground because they're not on the ground, but here, because we have this wire that is attached to the bottom of the string, we have something called a tension force. And the tension force always acts away from the center of mass along the wire or the string or the chain that has the tension. So in this case, it's going parallel to the wire, right? And because the child is being held here, and we know that these the forces are balanced, we need another force here. There it is, and it's a reaction force, and it must be the force that the person is holding. They're pulling the child slightly backwards just to keep it holding there. Now, I'm going to talk about how we know that that's true just after we've seen a couple of these diagrams. So this is our free body diagram here, but when we want to do actual problem solving with these, we like to put them without the diagram and just the arrows. So on the right here is now my free body diagram. Now I've talked about this person here, the child is not moving. If they're not moving, or if that means they're at a constant speed. If they're at a constant speed, all their forces must be balanced. Now what that means is, if we were to take all of our forces, let's take our tension force, and we add them tip to tail. Okay, so let's add our gravity force tip to tail to our tension, and our reaction force to the end of our gravity force. We've now followed the path of a triangle back to where we started. When we add all of those three forces up, we have gone nowhere, or we have a net force of 0. These forces are said to be balanced. So it's a very important skill to be able to take the forces from our free body diagram and put them into a triangle. Also, we need to recognize when things are balanced. Look at another example. Okay, so here's a skateboarder going down a ramp. Let's draw the forces acting on the skateboarder. Rule 1, center of mass. 2, gravity. 3, let's draw the reaction force, but notice it's a ramp, so the reaction force is perpendicular to the ramp, 90 degrees to the ramp, so it goes in that direction. Those forces do not cancel each other out perfectly, so there must be another one acting, and that's the friction force parallel and opposite to the direction of motion, parallel to the surface. There it is. Remember, our free body diagram is just a simplified example of this. And because this skateboarder, well, if the skateboarder is traveling at a constant velocity downwards, and I haven't said that they are, but let's assume that they are, all of the forces will add tip to tail until they're balanced. So that now is that's a triangle that shows us the balanced forces. Important to notice, we remember that the friction force and the reaction force are at 90 degrees to each other, so we've actually got a right angle triangle here. Okay, so one last example. Here it is. This is my picture of a ship attached to a wharf. The ship is actually the grey thing, the wharf is the brown thing. And here are two tugboats, the blue things, tugging at the ship. So there are three forces acting on this ship. And we can draw a diagram for this. So we draw the centre of the mass with the three forces. Particularly, I want you to notice, we don't draw the arrows where the actual ropes are attached. We draw the forces coming from the center of the mass and the direction that they would be acting. So in this case, there are three tension forces. There is the tension of the rope attaching the ship to the wharf and the tension of the two other ropes attached to the tugboats. Then we can draw a free body diagram for this, and assuming the ship isn't moving, they should again go tip to tail following each other. So these are free body force diagrams. This is how we draw them, and if any time that this object is balanced, all of those forces should follow and make a perfect triangle. Well, if there's more than three forces, it's not going to be a triangle, but they will go tip to tail and end up at the same place that they started. Okay, thanks for watching this video, and I hope that it has helped.